Right now, sitting perfectly still, you're moving through space at about 2 million kilometers an hour. Not the Earth around the Sun, the whole Milky Way. Our entire galaxy is racing in one specific direction through the universe. For a long time, we thought we knew what was pulling us there. We were only half right. Something is also pushing us, and the newest measurements of that motion have turned up a problem. We are moving faster than the laws of our universe are supposed to allow. So what is shoving our galaxy across the cosmos, and why is it moving too fast? Start with what we already knew. Our galaxy is being pulled. If you've seen our video on the Great Attractor, this is the other half of that story. The Milky Way and our whole local group of galaxies is falling toward a region in the direction of the constellation Centaurus. First toward the Great Attractor and beyond it toward the Shapley Concentration, the densest collection of galaxies in our part of the universe. Tens of thousands of galaxies all heaped together, their combined gravity reeling us in. That motion is real and it's fast. Compared to the leftover glow of the Big Bang, the cosmic microwave background, the most still reference frame we have, our galaxy is moving at around 630 kilometers every second, 2 million kilometers an hour in a fixed direction our entire lives, and we never feel a thing. For decades, everyone assumed that the pull was the whole story, that some big overdensity of galaxies was simply dragging us in. Then, in 2017, three astronomers, Yehuda Hoffman, Brent Tully, and Daniel Pomarede, mapped the motion of thousands of galaxies in 3 dimensions and found something nobody expected. We're not only being pulled, we're also being pushed away from a vast region of space that is almost completely empty of galaxies. They called it the Dipole Repeller. Now, how can emptiness push you? Nothing has no gravity. The trick is that it's relative. Imagine standing on a hillside between a crowded city and a deserted plain. Gravity is pulling everything toward the crowd. So, compared to all the matter streaming toward the dense side, you drift away from the empty side, as if the emptiness was shoving you off. An absence of gravity, on a cosmic scale, behaves exactly like a push, and it sits almost directly opposite the Shapley pole, on the far side of the sky. So the two line up into a single push-pull axis that runs right through us. The astonishing part is the balance. The push from this void and the pull from the Shapley are roughly equal partners in our journey. This push and pull is what defines our address in the cosmos. The same team had already used the galaxy flows to map our home supercluster, a structure they named Laniakea, Hawaiian for immense heaven, containing 100,000 galaxies including ours. The way you find its borders is by tracing the flow lines, the streams along which galaxies drift. We sit on a kind of a cosmic watershed, a giant emptiness on one side pushing us, a giant overdensity on the other pulling us, and our galaxy riding the slope between them. It's one of the most striking things modern astronomy has produced, a map of our cosmic neighborhood, drawn not from light, but from motion itself. For a few years, that was a tidy, almost beautiful picture. Push, pull, balance. We had mapped the forces moving us and given them names. And then, the measurements got better, and the picture stopped being tidy. Here's what changed. Astronomers tracked this large-scale motion with a number called the bulk flow. Basically, how fast a huge sphere of the universe is collectively streaming in one direction. And our standard model of the universe makes a firm, testable prediction about it. The model says the universe is smooth and the same in every direction once you zoom out far enough. So the bigger the region you average over, the more all these individual motions should cancel out and the bulk flow should fade towards zero. Calm, still, uniform. Using the newest catalog of galaxy distances and velocities, called Cosmic Flows 4, a team including Richard Watkins, Hume Feldman, and Brent Tully measured that bulk flow on enormous scales. They did not find it fading, they found the opposite. The motion gets faster the larger the volume they measure, rising exactly where it should be dying away. We're talking about regions hundreds of millions of light years across. So large that on the model's own terms, everything inside should have settled into near stillness. Instead, all of it is drifting the same way, as if some far larger hand was sweeping the whole neighborhood along. The size of that motion, on the biggest scales they can reach, has less than 100% chance of happening in the standard model. The mismatch is sharp enough that it's hard to wave away as a fluke. So what's going on? There are two honest possibilities, and each one is a big deal. The first possibility is that there's far more out there moving us than we've mapped. Bigger attractors and bigger repellers beyond the edge of our charts, reaching across hundreds of millions of light years to drag and push whole regions of the universe, including ours, in a coordinated stream. The Shapley pull and the Dipole Repeller push might just be the nearby parts of something much larger we've not yet seen. In that case, the universe is even more structured than we thought. A deeper hierarchy of attractors and voids stacked on top of one another, and we have charted only the bottom rung. The second possibility is heavier. Maybe the assumption itself is wrong. The idea that the universe is smooth and the same in every direction on the largest scales is called the cosmological principle, and it's one of the foundations the whole standard model is built upon. It's the same assumption the Big Ring and other giant structures have been quietly straining. If the bulk flow really keeps rising, it's one more crack in that foundation, a hint that the universe is lumpier and stranger than our tidiest model allows. And that would not be a small repair. It would suggest the cosmos does not look the same in every direction on the largest scales, which is something the standard model simply does not permit. What makes this exciting is that it's not settled, and it's not stuck. Every new release of galaxy motion data sharpens the measurement, and astronomers are genuinely arguing about it right now. Some think hidden systematic errors will shrink the tension. Others think that it's real and growing. A new generation of sky surveys is already measuring the motions of millions of galaxies, far more than the catalogs that first raised the alarm. And they will push the number one way or the other within years, not decades. And sit with what that means. Our own motion, the direction our galaxy happens to be falling, has become a tool for testing whether the universe is as uniform as we assumed. The thing that carries us through space might also be the thing that redraws the map of everything. So here is where it leaves us. You're sitting still and you're not. You're being pulled toward the largest concentration of galaxies we can see, and at the same time pushed by the largest emptiness near us, racing somewhere at 2 million kilometers an hour. And we have just discovered that we cannot fully explain the speed. The forces that move us are partly mapped, partly mysterious, and possibly a sign that our picture of the universe is incomplete. This channel is about exactly these moments, where something as settled as a galaxy's motion is quietly hiding a question we cannot yet answer. If you want to be here as the data comes in, subscribe and stick around. Until next time, clear skies.